Hey everyone, in this video let's take a look at question 5, longest palindromic substring on Leetcode. This is part of our blind 75 list of questions, so let's begin. In this question we are given the string s and we want to return the longest palindromic substring inside s. So we're actually not supposed to return the length but the actual value itself. Let's take a look here at the examples to see what we're working with. So in this one over here we have a couple of them, right? Like we have the string BAB, really just BA, D, like these three in themselves are like considered substrings. We also have like ABA, etc. So the longest one is BAB or ABA, and actually any of them would be a valid return here. In something like this one, it would just be BB. Looks like this is the valid one. And really, if there's nothing, like there's no common letters, maybe something like this, then the valid one would be either Q, W, or E. So those would be the three valid ones. So how might we go about doing this problem? So let's take a look. Maybe if we have I don't know. Let me think of a. Let's just say we have AD, and then maybe we'll have like a EEE, and then maybe we'll have like a D here, and then maybe this is like PQ, something like this, right? So if this is our substring, and let me join them together right now. So if this is our string in its entirety, and we want to find the longest palindrome, well, I'll tell you right off the bat, there is one solution in this problem that uses something called expand around corners, expand around centers, I think it's called. Like the solution over here. I didn't really think of that one, and I think during the interview, like expand from centers, yeah, I wouldn't really even think of this one, so I'm not gonna talk about that one. But the approach I do want to talk about is a recursion one or dynamic programming one. And I don't want to just say that, but like I want to motivate why kind of that might be appropriate here. So if you kind of think about it, right? Like so we have this substring over here, or we have this entire string over here. In order for us to like even find the longest palindrome, it would make sense for us to like figure out which one of these substrings themselves are palindromes, and then based off of like the length of that substring, we could determine which one is the longest one. So really, if you think about it, this problem can be broken down into figure out all of the locations that form valid palindromes, right? And essentially, if it forms a valid palindrome, then it's a potential candidate to be the longest valid palindrome. And so then we can go ahead and add it to our answer if it's appropriate. So in a lot of these string type questions, whenever you're dealing with two strings, kind of just a pattern, this is just one of the patterns that you have. So if you're dealing with string 1, maybe it's something like this, and dealing with string 2, maybe it's something like this, whatever, and you want to do operations on two strings, then usually you have like an I pointer here, or corresponding to this one, you have a J pointer here corresponding to this one. So this will essentially like allow you to traverse both of the strings when you're doing your recursive solution here. But usually when you have just one string, then you have an I pointer at the start and you have a J pointer at the end. And so what you do in your recursive call is at the start, you want to determine if like this is a palindrome, and we don't know that yet, right? So in order for us to even determine this, and actually let me put this as A just to kind of motivate a point, but we don't know that yet. So what we do is we move in our I and J pointers to determine eventually if something is a palindrome or not. And so if we arrive at the value that something is a palindrome, then it's potentially one of our longest palindromes, so we can consider it. So that's kind of where recursion comes from. It's the idea that in order for us to find the longest palindrome, we have to figure out all of the list of palindromes. And so we can do that using recursion, which is actually better than the iterative case in which you would like brute force all of the list of palindromes. Okay, so how might we go about like finding the list of palindromes, or whether like something is a palindrome or not? So let's see here. If we start off I over here and J over here, well, what do we know that has to be true about a palindrome? Well, if we have a palindrome, let's say like just like race car, for example, we know that each of the letters, for example, this letter here maps with this letter here. This letter here is the same as this letter here. So in order for us to really determine if something is a palindrome, if you kind of think about it, let's say S at I is equal to S at J, right? So this element here is equal to this element here. Now, this is not the question longest palindromic subsequence, but in this one, rather, it's longest palindromic substring. So what that means is that in order for these two, if these two are the same character and we want to include them in our palindrome, then this entire thing really has to be a palindrome, right? This entire thing. We can't just have like this middle part be a palindrome. That's a different question. That's longest palindromic subsequence. But this is substring. So what it means is that if these two are palindromes, we also require that this entire thing is also palindrome. So if you think about it, if this is true, if S at I is equal to S at J, then our recursive call, basically from S at I plus 1, or I guess like recursive call, I plus s and then I plus 1 and the j minus 1, this should also kind of be a palindrome, right? If you think about it, if this is a palindrome and we've concluded that these two are the same, then we know that this entire thing is a palindrome. Okay, so we've made like one inference so far, so that's good. Now, let's assume here that actually maybe this instead was a p, right? So let's assume here that maybe this was not a palindrome, right? So this was not a palindrome. So like A and then P, it doesn't match. Okay, so if it doesn't match, what are some of the things we could do? Well, if you think about it, if it doesn't match, then I have like two options, right? And this is common in terms of like our string type questions. Either I can consider maybe this string here without this last character here and maybe see if like this is some sort of palindrome. Like for example, maybe this was at A and so then this and this would match and then we would look inwards to see if this is a palindrome. So maybe we could do that. Alternatively, maybe we could consider this string over here. So we exclude the A over here and then maybe this P actually matches with this P over here. And so if these two match, then we want to check if this inside value here is a palindrome. So those are like our other cases. So we can check like also, so basically if S at I does not equal S at J, right? Like if this is false, then what can we do? Well, in this case, essentially, we could check to see recursive call S at I plus 1 and J. So in this one, we consider something like this. And we can also consider recursive call S and then I and then J minus 1. J minus 1. So in this one, we're considering this string over here. And maybe this is the palindrome. Now, notice that if any of these two are palindromes, it does not mean that I to J is a palindrome, right? I to J is not a palindrome. That's why we're considering something like this. And so that point will be like more important later on. But let's see if we can come up with the algorithm, like recursive algorithm, so that we can solve this question. And then we can see how we can improve this using dynamic programming. So let's maybe start off with the recursive algorithm. So let's go ahead and do that. Okay, so what do I need? So my string here looks like it's length 1, so I don't have to ever check for length 1 at the minimum, so I don't ever have to check for empty. So maybe something I could do is I could have my result variable here, and my result variable maybe in the start, we can have it like just s at 0, because as we argued here, at the minimum, the palindrome is like one letter, right? So we can just set it equal to s at 0. And then what I'm going to do is I'm going to have my helper function here, and my helper function is going to go through this entire string. It's going to find palindromes. And for example, maybe like this entire thing was a palindrome, right? Or maybe this is a palindrome here. It's going to compare the length of that string. And then if it's greater than res, then it's going to append it, or it's going to update res. So maybe here actually I can do self.res, so I can refer to it from inside of the helper function. And we need to do self so the value doesn't change like when we do recursive calls. So we can do that, and in the end we'll just return self.res. Now I have my helper, so what do I need? So I have my self, I have my s. Looks like I need my I and j, right? I need my I and j. And I think that's pretty much actually all we need in this case. Okay, so let's consider the case where like, let's see, what if I is equal to j or I is greater than j? So for example, like what if I and j, maybe I is over at this e here and then j is also at this e. If you kind of think about it, if I is equal to j, then this has to be a palindrome, right? Like in this function, what we're doing is returning if something is a palindrome or not from the indices I to j. So you can see here that this has to be a palindrome, right? And really, even if like this was out of bounds, right? For example, if we just had one letter to work with, and then here we went like I plus 1, j minus 1, then we have the empty string, right? So this is kind of also out of bounds. So really, if you think about it, like if I is equal to j, then we can return true. Alternatively, if I is like greater than j, we can also return true. So that's kind of like our two base cases here. Now, let's consider this case. So what do we have here? Well, here we have if s at I is equal to s at j. If this is the case, right? If this is the case, then what? Well, we want to check that this recursive call here from I plus 1 to j minus 1 is also a palindrome. So we can actually extend this. So we can maybe just do if s at I is equal to s at j and what? And s at I plus 1, or I guess recursive call here, right? S and then I plus 1, j minus 1. So if this value returns true, so what does this mean? Well, first of all, it means that this inside value, so let me actually revert these. So my I will be over here, and then this j will be over here. So if these two values are the same, I and j, these two values are the same, the a and a, and this inside is also the same, it means that this entire thing from I to j is a palindrome. So what does that mean? Well, it means that I can take the length of this palindrome and I can see if it's greater than res. And if it is, I will go ahead and update res. So I can do if j minus I, remember we're doing from right-hand side minus left-hand side, and you actually have to do +1 here, simply because of like the way indices work. Like for example, if I and j were both at the same index, then this is actually 0, but the length is actually 1. So you have to like add in the 1. So if this is greater than the length of self.res, then I'll update self.res to the substring from I to j plus 1, I to j plus 1. And then I will go ahead and I'll just return true here. Now, what about the case where this is false? Well, if this is false, then we have to essentially check I plus 1 and then j minus 1, right? So we have to check these two locations here. So I will do helper s I plus 1 j, and then self.helper s I minus 1 this should be I and then j minus 1. Yeah, so that's what it will be. And notice that these two, even if they return true, right? Like I don't really care, right? That's not what I'm interested in, because maybe this is true, but I can say nothing from like I to j. From I to j, the value is false, right? This recursive call here is dealing with I to j. So if you think about it here, like I would still return false, but maybe if I do like I plus 1 to j, right? So maybe I'm considering like this value here. Maybe if this is true, then somehow it'll get updated in here. So we'll still be updating our res call. And so if you think about it here, all I need to do is pass in just s and then 0 and then length of s minus 1, just to kind of reiterate like what I'm doing here. So this recursive call all in itself will return true or false depending on whether the substring from I to j is true. It is a palindrome. We know here that if I is equal to j, if the first and last element agree, and the middle elements are also agreed as per the recursive call, then this entire thing is a palindrome. So I can go ahead and return true, and I can update my res from I to j plus 1. But if that's not the case, then I will consider from I to j minus 1 and from j to I plus 1. And maybe this is a palindrome in itself. I don't know. But I can't do something like left is equal to this and the right is equal to this and then return left or right. Like this would be incorrect, because I can't do that, because at this recursive call here, all I'm dealing with is from the indice I to j. So I can't say anything. Like if this is true, then I can't say anything about the I and j, right? The only thing I can say is like that it's false, because I to j is definitely false because we passed this one. But we still should look at I plus 1 to j and then I to j minus 1. And maybe when we do something like this one, we'll actually end up in a scenario. So actually in this one, like I and then j, this is equal, and then we'll look inside of here. And maybe if this is the same, which it actually is, then we'll actually go ahead and update this entire thing as our substring up to res. And so that's what we do here. So that's the solution here. So let me go ahead and start it off, and then we can see how we can improve it and then do a dynamic programming type solution. Then go ahead and submit it here. Now, this one automatically, I'll just tell you, it becomes a TLE. So how can we improve this? Well, after recursion, the next basic step is to do memoization, right? So we can cache things in our memo. So let's go ahead and do that. I have a memo call here, and in these two. So we can see we got a TLE. So I'll pass in the memo. Now, what do I need to cache into the memo? Well, take a look. What is changing, right? It looks like the I and j is changing. So that's what I need to cache in my memo. So what I can do is here, I can actually do memo at I and j is equal to true. Here, at the very end, memo at I and j is equal to false. And then here, I can actually just check. So if I and j in memo, then I can return memo at I and j. And we've done these memoization before. And memo is a dictionary. So now let me go ahead and run this to see what we get. Okay, so it works. So let me go ahead and submit it now. So I believe this will still work, but it will be extremely slow. So let's just confirm that. You can see that the last one I did, it took like over 7 seconds to do. And I think this one was with memoization. So let's just wait to see that this one, I think it still passes. Okay, so it does. So it takes 8 seconds, which is way longer than it needs to be. So how can you further improve this? Well, we can use dynamic programming. So let's see how we can do that now. Okay, so in dynamic programming, it actually becomes much easier once we've done the memoization, because it tells us like what we need to do, right? If you think about it, dynamic programming, all we're doing is we're caching the memoization result, but in terms of a DP array. Okay, so now we have to ask ourselves, what should be the size of the DP array and what should be like the default value? Well, if you think about it, what is the size of the memoization? It's two variables, right? So it's 2D here, and kind of both of them have to deal with this substring over here. And just think about like what exactly this is doing, right? This is saying that, for example, if memo at like like 3 or like 4 to 9 is equal to true, this means that the substring from S 4 to 9 is a palindrome. That's what it's saying. So if you think about a dynamic programming array, it has to be a 2D array. So how can we define that? We can do something like dp, and then initially you can see here that actually it should just be false, right? Because we want to return true, or we want it to be true if it is a palindrome. So it makes sense to start it off at false. So I can do false. So what am I doing here? I'm basically creating it of size. Looks like I'll just start off with length of S, and I'll see if I need to improve it or like expand it by 1, but I think I should be fine here for range 0 to length of S. So this is just creating an S by S DP array. And what does it mean? Well, let's just take a look here to see like what it means. So for example, let's say we had, let me maybe just create a quick DP array. D and then, oops, A and then R. Okay, so let me quickly do that over here. Sorry. Okay, so let's assume that our word is something like a race car, right? So let's assume that our word is something like R, A, C, E, C, and then A, and then R here. And then similarly here, the word will be race car. So R, A, C, E, C, A, R. Really, when we're doing dynamic programming, these should be like the indices. So this should actually be like index 1, index 2, etc., like all the way forward. But just kind of doing it like this, it's just easier to see. Now, one thing we know about this DP array, first of all, is like the only values we're really considering is the ones that lie like over here and then above, right? Because if you think about it, like, for example, if I start off at this A here, then this cell over here refers to the string AR, which doesn't really exist, right? It exists like all the way here, but that's not like what we're considering. So for example, like this string over here, like let's say this string over here is just the string R. This string over here is a string RA, and then this is RAC, etc. And this entire thing is the string race car. Now, what about this string here? Well, this string is, if you think about it, it should be like A and R, right? But it doesn't make sense here because A and R is not even like a substring. So rather, we would start from here, and this is A, and so then this is AC, and then this is ACE, etc. And then this would be ACE-CAR, etc. So like that's how we're forming our list of substrings, if you think about it. And so what we're really considered with, or what we're really interested in, is all of the values from here above, right? All of these values over here. And our answer will be, well, we actually don't like know where our answer will be, because if I look at this cell over here, all this will tell me is whether race car in itself is a palindrome. But I don't really care about that, right? I'm just trying to find where the largest palindrome is. So in that sense, we will actually just go through each of these. And what we can do is we will mark off an individual cell. And if we mark off an individual cell, for example, if we mark off this cell, what it means is that the string ACECAR, ACECA is a palindrome, which in this case it actually is. So we'll go ahead and do that. And so let me erase a couple of things here so we can go ahead and move. Okay, so we have that information. So we have our DP array. Now, what's one thing we notice automatically? Well, one thing we notice is like this central diagonal over here. It's just this one letter, right? It's just C and then C. Here it's just E and then E, C and then C, etc., A and then A. So if you think about it, if I just have like one element, which is just this central diagonal here, then the value has to be true, right? Because that in itself is a palindrome. So really how I can do this is I can do for I in range 0 to length of S, and then DP at I has to be true, right? Because what we're doing is in this scenario, we're just considering the string C and then actually not there, right here, C and then C. So this is a palindrome. Similarly, this is, etc. So all of these are palindromes. Okay, so now what? Well, take a look here, like what we need, right? So we have the following conditions that we need. So before like you create any sort of DP array, it's important that you know like how you're traversing, and so that would actually tell you if you need to somehow extend your DP array size or like and how you need to traverse. So we have a couple of things, right? So we need to know I plus 1 j minus 1. We need to know I j minus 1, and we need to know I plus 1 j. And where did I get that? I got that from our memoization, or recursion. I guess I can't minimize if I have that. I got them from here. So I plus 1 j minus 1, which is what I have here, I plus 1 j minus 1, and then I j minus 1, I j minus 1, the second one, and then I plus 1 j. Okay, so what does it mean? Well, it means that, for example, if this is I, which is my set of rows, and this is my j, which is my columns, let's say I'm looking at this cell over here. Let's say I'm looking at this cell over here. Okay, so what do I need access to? Well, I need access to I plus 1, j minus 1. So what cell is that? So maybe let me do it in, I'll do it in this color. Okay, so what is I plus 1, j minus 1? Well, I plus 1 is down here, right? I plus 1, and actually maybe I can just write that out so it's easier. It's also easier for me. So this is cell I plus 1, this is cell I minus 1, this is cell j minus 1, and this is cell j plus 1. Okay, so if we're at this purple cell over here, then I plus 1 and j minus 1. So I need I plus 1 and j minus 1. So I need access to this actually. Okay, now what else do I need access to? Well, I need access to I and then j minus 1. So my I remains the same and then j minus 1. I need access to this. Okay, what else? Well, I need access to I plus 1 j. So my I plus 1 and j, so this value over here. Okay, so we can basically see that we need access to like the right hand side, this diagonal under like to the bottom left and just below it, right? So we need access to these three things here. Now, if you really think about it, like for example, if I'm like all the way up here, right? If I'm all the way at this, maybe I'm at like this cell over here. If I'm at this cell over here, let me do it in purple. Well, okay, do I have access to everything? I do, right? Because I have access to, no, I actually don't, right? I have access to this, I have access to this because these are in the diagonal, but I don't have access to this value over here. And actually, I don't even need to consider it in this one, so maybe this was a bad example, but let me do maybe this one. If I'm over here, do I have access to everything? I have access to this one, maybe if we're like traversing from left to right, sure, but I don't have access to this cell, I don't have access to this cell, and I don't have access to this cell, right? So basically, given that we need this information, this gives us a way to understand how we actually need to traverse through our DP array. We can't traverse from a traditional left to right, row by row, column by column. We can't do that because I won't have access to these values when I need them. Okay, so what can we do in this case? Well, often like when you have a case like this, the way to actually traverse is in the reverse order, right? You need to traverse in the reverse order. So what that means is, for example, if we've already filled up all of these like cells over here, then I can actually start off and I can traverse from this cell over here. And so what does this mean? Well, if I know this one, I know this cell over here, I know this, and maybe here I can just like put like an empty value, right? Like false, because this cell over here I actually don't even need to consider. Remember, we're only considering the cells that are here and then above. So really here, like this is just false, right? So maybe I can actually append on one more row to this. And so if I append on one more row, then you can kind of think of it as like I'll have access to this value here and I'll just set it equal to false. And then what you do is you might have to like learn a pattern here, but basically after we're done this one, then I can go ahead and I can process this cell, right? Actually, no, I can't process that one because I actually need to process this one next. Because then I'll have access to the cell on the left, this one, and then this underneath one. Again, I can just go ahead and I can just like create one more size array. So then what I could do is then I could go ahead and process this cell over here, and then I have access to all three of these, and then I repeat. So then I can process this cell over here, and then I have access to actually all three of these, right? I have access to this, I have access to this, and I have access to this value below. But basically, you can see that like as we are traversing in that sense, we're able to traverse through the entire array. Okay, so let me actually go back and erase a lot of this as far as I can go. Okay, so what did we discuss? Well, we discussed that really we're just interested in these values over here, right? These values over here. And if I start off at this value over here, because we already know this entire diagonal, well then I don't have access to this value over here. So what did we say? Well, we said that we can maybe increase our DP size by 1, and so like our array by 1. So if you think about it in that sense, what's going to happen is like maybe the number of rows we can, I guess here, actually, let me think. No, I guess actually we have access to this one, right? We have access to this. Yeah, we do have access to it, yeah. Sorry, so I guess we don't actually need to even increase the size because we have an R over here. So really, I think we can just keep our size as it is. Yeah, I think we can keep our size. We were never going out of bounds, because if we had to maybe process like this cell over here, then we would have to go out of bounds, but like access this cell over here. But because we don't have to do that, because like this one is already filled in, then we can actually just start off by traversing at this location here, and then we have access to like all 3 of these. And so, okay, so in that sense, it doesn't look like we have to increase the size of the array. Perfect. So let's take a look at how we can do that. All right, so I already filled in my base condition here, where dp of I at I is equal to true. And you can kind of see that this is like what we have here. Now what do I need to do? Well, now I need to traverse in reverse. So I'm actually just going to create my my variables here, rows and columns. So what am I doing here? Well, traversing in reverse, right? So essentially, I'm traversing from not row -1, but row -2, right? So that's the location I'm traversing from. So I can do for I in range, I'll traverse from rows minus not 1, because that's the last row, but 2. The last row, because we can't traverse that because it's this entire thing here, but 2. So we want to traverse this one. And what about the column? Well, I want to start at like the first hand, right? So for example, I want to go from here, here, and then here, 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 here. So what is the column I'm starting off at? Well, the column, if you think about it, the column will be, well, whatever the row is, right? So for example, this row here, what is this row? 0, 1, 2, 3, 4. Row 5, right? Row 5. So, and which column do I want to start off at? 0, 1, 2, 3, 4, 5, 6. So I want to start off at I plus 1, essentially, right? I plus 1. So I can do something like this. And then actually, I don't think here I need even this. So I can do for j in range, I plus 1 to the end, right? So I guess that's where I had the columns. For j in range, I plus 1 to the end, which will be basically columns, right? Columns. Now here I actually need to, so this is our loop. Now what do I need to do here? Well, I need to loop from the bottom row all the way to the top, and I need to consider like the top, right? So I would do from here to -1 and then -1. -1 because we want to go to like, we want to process row 0. So that's why we need this one here. Okay, so let's just take a look and just see that I have the indices correctly. I just want to kind of see that. So let me maybe enter my string as something like race car, just to kind of see that I have my indices correctly. I don't know if I do. Okay, so 5, 6, that's correct. And then we'll go up, so 4 and then 5, and then it should be, and then 4 and 6. Okay, perfect. And then we repeat. Okay, so it looks like our indices are here correct. So then after this, it actually becomes very simple, because all we need to do is what we've done exactly here. So first of all, I can check, right? So I can check if s at I is equal to s at j, right? So if this is the case, then what? Well, then I know that these values are the same. So then I want to check if dp at I plus 1, j minus 1 is the same. Okay, so what can I do in that case? So I can actually check. I can check if this is the case, and dp at I plus 1, j minus 1. If this is true, then what? Well, then I know dp at ij is equal to true. But then also, I can calculate the difference. So I can do if j minus I plus 1 is greater than length of self.res, then I can just update self.res. And here I can just keep it as res, but I'll just leave it here to, and then I, and then j plus 1. Okay, so that's that case. Otherwise what? Well, otherwise, I can just go ahead and do these calls here. Well, in order for me to like do these calls, notice how I'm not like returning anything into them, right? So essentially like what I could do here is I would have to still consider these, but the question is like, how do I consider them, right? Because in here, like we're setting the value to true, but otherwise what can I do? So what can we do here? Well, it turns out that luckily we don't even need to consider these two cases here. And the reason is because we're actually not returning from them. So like we're doing the recursive call, but that's already all captured in this DP array here. Because if you think about it here, when we're doing the recursive call, really the bulk of the update happens when we do something like this, right? So we don't even need to consider I plus 1j and then I and then j minus 1. So even though we don't need to consider it, like consider it, if you kind of think about it, like for example, if we're at like this value here, then the thing we do need to consider is I plus 1 and j minus 1. So we still need to consider this cell over here. So we're still like looping in the correct way from the bottom all the way to the top. But it's just that we don't need to consider these two cells over here. Okay, so like that's one good news. Now we're almost done, but there's actually one edge case that we have to look out for. Now, what would that edge case be? Well, what happens if, like, for example, I and then j here, let's say they have like a distance 1 away. Like let's say they're two letters, right? So maybe here, maybe let's say this was a, right? Just for practical purposes, let's just say this was a. So what would that mean? Well, that would mean that this value over here should equal true, right? So if you think about it, what does this value over here represent? Well, it represents the string a, right? So this value should be true. So if you think about it, this I and then j, these two values are equal, but the I plus 1, j minus 1, this value here is actually false, right? And that's just one of the edge cases that we have to worry about because like we're on this boundary over here. So all of this here is already false. So even if these two values are the same, something like here would be false. So that would return false. So the way we can kind of get around this is we can do if s at I is equal to s at j, and either this is true or maybe j minus I is equal to 1. So like they're two elements essentially, like and they're both the same, then we know that it's a solution. Then we know that it's still true. So we can go ahead and submit this to hopefully arrive at the answer. And so this video was extremely long, much longer than I wanted, but really this question was the one that troubled me in terms of like dynamic programming and recursion. So I hope that I was able to explain in a way that made sense. But essentially, like we started off with recursion, we memoized it, and from that we understood the dynamic programming approach. We understood how to like go through the array in reverse order. We basically just ignored these calls over here because we don't need to do them. They're not returning anything, so we wouldn't even know what to put in here. Really, technically they are, right? Like they're returning false. So if you like think about it, like we don't really care what we want to do there, but the entire array is already false, so we can just save ourselves that recursive call. And so that was this question. For the time, it's basically just O of n squared. It's kind of like half of that because you're just going through half of the array, but really you can take that as you will. And then for the space, it's again, same thing, O of n squared. Okay, thanks for watching.